In this video, we're going to learn about probability. This will build on your knowledge at GCSE, specifically on sets and Venn diagrams and conditional probability. If you want to refresh yourself on these two topics, I'll put links to my videos on them in this video's description, but I am going to assume you know the knowledge from each of these videos. Before we begin, we need to talk about one main difference between the two exam boards AQA and Edexcel. At AS level, the board AQA uses set notation, so if we had these Venn diagrams here, they would say that this is the intersection of A and B, the union of A and B, and the complement of A. Edexcel, on the other hand, doesn't use set notation until the second year of A-level study. So for this video, we will refer to this set as A and B, this set as A or B, or for some clarity, A or B or both, and this set as not A. You just need to be aware that if your exam board is AQA, you'll use these symbols instead. The two main ideas at AS level for probability are mutually exclusive events and independent events. We'll start with mutually exclusive events. These are events that cannot occur at the same time. What this means is if we had two events A and B, which we knew were mutually exclusive, if we drew a Venn diagram of their probabilities, then this overlapping section here in the middle, which is the probability of A and B, must be equal to 0, since these two events cannot occur at the same time. If this is the case, then we can actually draw the Venn diagram slightly differently by removing the overlap from the circles altogether. So the left circle is now just the probability of A, and the right circle is the probability of B. A consequence of this is that if you're working out the union, or the probability of A or B, you can just add together the probability of A and the probability of B. This won't work, however, if the events are not mutually exclusive. In this diagram, the probability of A or B is this region here. If we said that this was equal to the probability of A plus the probability of B, then we would do the probability of A, which is this circle here, and the probability of B, which is this circle here. And you should notice that we've counted this overlapping section in the middle twice, so this can't be equal to the probability of A or B. We can make one addition to this formula though. Since the overlapping section in the middle was counted twice, and that's the probability of A and B, we could just subtract this, and the formula will now be correct. This is something that you will look at more in your second year of A-level study. So to summarise, if two events are mutually exclusive, then we have the probability of A and B equaling 0 since there's no overlap, and the probability of A or B is the sum of the probability of A and the probability of B. Let's take a look at some mutually exclusive events. Imagine we rolled a dice, and we said that A is the event that a prime number is rolled, and B is the event that a square number is rolled. A standard dice has 6 numbers from 1 to 6. So looking at event A, the prime numbers are 2, 3, and 5. So if we rolled one of these numbers, we'd say we've got event A. For the square numbers, for event B, we've got 1 and 4. So if we rolled one of these numbers, we'd say we have event B. Notice how events A and B cannot happen at the same time, since there are no numbers on the dice that are prime numbers and square numbers. They are therefore mutually exclusive. We also have the number 6, which doesn't fit either of these events. So if we were to draw a Venn diagram to represent the probabilities of these two events, we know that since both of them cannot happen at the same time, the probability of A and B must be 0, so we could write a 0 in the overlapping section in the middle. Since there are 3 prime numbers, the probability of event A is 3 over 6, so we could write that in the A circle. And for event B, there are 2 square numbers, so we have 2 over 6. And of course there's one number, the number 6, that doesn't fit either of these events, so we have 1 over 6 on the outside. So we could draw the Venn diagram for these two events in this way, or since the probability of A and B is 0, we could actually separate those two circles and draw it like this. Next we're going to take a look at independent events. Events are independent if one event happening does not affect the probability of the other happening. For example, if we had a dice and a coin, and we rolled the dice and flipped the coin, the outcome of the roll on the dice doesn't affect the probabilities for the outcome on the coin. If I rolled a 5 on the dice, that doesn't somehow change the probability of rolling a heads or tails on the coin after. The same happens in reverse. Flipping a tails on the coin doesn't somehow change the probabilities of the roll of the dice. These events are therefore independent of each other. Another example might be the month that you're born in, for example it could be September, and whether or not you're a subscriber of this channel. It doesn't make sense to say that these two events are somehow dependent on each other. Whether you're subscribed to this channel or not clearly doesn't depend on which month you were born in, although if you were born in September, why not subscribe? Sometimes though, events are dependent on each other. For example, if we had this bag of counters and we were going to take 2 counters from the bag without replacing them. the probability that you select a blue counter on the second pick will depend on the outcome of the first pick. For example, if on the first pick we got a blue counter, the probability of a blue on the second one is now 3 out of 8. But if instead the first pick was red, the probability of a blue on the second pick is now 4 out of 8, since there are 4 blue counters remaining. So the probability of selecting a blue counter on the second pick is entirely dependent on the outcome of the first one. For another example, let's imagine we randomly select a student from a school. Let the first event be the probability that the student selected is over 6 feet tall, and the second event be the probability that this student is in the school's basketball team. In a sport like basketball, taller players have a physical advantage, therefore taller people tend to make up most of basketball teams. This doesn't mean that all tall people will necessarily be in the basketball team, but it does mean that if the outcome of the first event is that the student is tall, then the probability that they're also in the basketball team is likely to be higher. These events are therefore dependent. When we have independent events, the probability of working out A and B will always be equal to the probability of A multiplied by the probability of B. For example, if we return to the dice and coin. The probability of rolling a 4 and then flipping a heads is simply equal to the probability of rolling a 4 multiplied by the probability of flipping a heads. The probability of a 4 is 1 out of 6, and the probability of a heads is 1 over 2. If you multiply these together, you get 1/12. This only works if the two events are independent of each other, which means we can use this formula to determine if two events are independent or not. For example, if we had this Venn diagram here and we wanted to know if the events A and B were independent, we could work out the probability of A and B, which is this overlapping section here in the middle, so 0.32. The probability of A is the sum of the probabilities from this circle here, so 0.08 plus 0.32, which is 0.4. And the probability of B is the sum of the probabilities from this circle, so 0.32 plus 0.48, which gives you 0.8. We can now test if the formula holds by multiplying together the probabilities of A and B. So the probability of A multiplied by the probability of B is 0.4 multiplied by 0.8, which is 0.32. And this does match the probability of A and B. So we could conclude that these two events are independent. Let's take a look at some exam-style questions on these topics. As a reminder, if the events are mutually exclusive, we can say these two things, and if they are independent, we can say this. So in this question, we're given 3 probabilities of A, B, and C, and we're told that A and B are independent, and B and C are mutually exclusive. The first question says, work out the probability of A and B. Well, we know that A and B are independent, in which case this formula here can be used. So to work out the probability of A and B, we'll multiply the probability of A and the probability of B together. The probability of A in the question is 0.9, and the probability of B is 0.7. If you multiply these together, you get 0.63. In part B of this question, it says work out the probability of B and C. Well, we are told that B and C are mutually exclusive. That means we can use this fact down here, although we'll need to switch the letters out from A and B to B and C, but the same thing applies. So since they are mutually exclusive, the probability of B and C must be 0. For part C of this question, we're asked to explain why events A and C cannot be mutually exclusive. So if they were mutually exclusive, then this formula here would hold with the letters A and C rather than A or B. So the probability of A or C would be the probability of A plus the probability of C. So let's test this out by adding together the probability of A, which is 0.9, and the probability of C, which is 0.2. If we add these together, we get 1.1, which is a problem since probabilities cannot be greater than 1. This means there must be some overlap in these two events, in which case they can happen at the same time, and are therefore not mutually exclusive. So we could say that 1.1 is greater than 1, so A and C cannot be mutually exclusive. Next, we're going to be given an extra piece of information. The probability of A or B or C is 0.99, and we are going to be asked to draw a complete Venn diagram for these 3 events. We know that B and C are mutually exclusive, which means they don't have an overlap. So we can draw one circle for B and one for C that don't have an overlap. Events A and B are independent, so they will have an overlap, and events A and C were not mutually exclusive, so they must have an overlap as well. So we need to draw a circle for A that overlaps B and C, so we can put one in the middle like this. If we then draw a box around this, this completes the structure of the Venn diagram. We just need to add on the probabilities. In the first part of this question, we worked out the probability of A and B, which was 0.63. So that must go in the overlapping section between A and B, so here. We know that the probability of B is 0.7, that means the sum of the probabilities in this circle here must be 0.7. Since we know the 0.63, we could work out the missing probability by subtracting that from 0.7. So 0.7 subtract 0.63, which is 0.07. So 0.07 goes here. Next, let's have a look at the probability of A, which is 0.9. That means the sum of the probabilities inside this circle must be 0.9. The problem here, though, is that we have two missing numbers. So we're going to label these with letters. Let's use P and Q. For now, we can't do any more with this, but we will return here soon. What about the probability of C being 0.2? That means the sum of the probabilities in this circle is 0.2, but unfortunately we don't know Q, so we can't find out the missing one either, so we'll give that a letter as well, so we'll call that R. And this leaves one more region, which is the outside part here, and we don't know that either, so we'll give that a letter as well. We'll call it S. In the question, we're told the probability of A or B or C is 0.99, which means the sum of all of the probabilities in all three of those circles must be 0.99, so all of these ones here. This also means that if we look at the complement of this, which is everything not inside the circles, so our probability S, must add with this probability to give 1. So we could do 1 subtract 0.99 to find the probability of S, which is 0.01. So S must be 0.01. Now let's return to these probabilities here, which we know sum to give 0.99. So we could write that as an equation. All of those probabilities added together equals 0.99. We can add the 0.07 and 0.63 to give 0.7, so we end up with this equation here. And then if we subtract 0.7 from both sides, on the left side it will cancel, and on the right side 0.99 subtract 0.7 is 0.29. So we end up with this equation here. At the minute though, there are too many unknowns to be able to solve that equation, so we need to form another one. Let's write an equation for this circle here. These three probabilities must add to give 0.9 since that's the probability of A. So 0.63 plus P plus Q must equal 0.9. If we subtract 0.63 from both sides, it will cancel on the left, and on the right we'll have 0.27. So we know that P plus Q must be 0.27. But P plus Q was also in this equation here, so we could substitute this out for 0.27. So we'd have 0.27 plus R equals 0.29, and we can subtract 0.27 from both sides to give R equals 0.02. So we've managed to find the value of R. Let's add this onto the diagram. Now if we return to this circle here, we can find Q. These two probabilities must add together to give 0.2 since that's the probability of C. So Q plus 0.02 equals 0.2. Subtracting 0.02 from both sides gives you Q equals 0.18. So we can add Q into our diagram. And finally, if we look at this circle here, these must add together to give the probability of A, which is 0.9, so we can form this equation here. If you subtract 0.63 and 0.18 from both sides, you find that P is equal to 0.09. So we can put that onto the Venn diagram as well, and the Venn diagram is now complete. Let's try another question where a Venn diagram has already been drawn for us. So we have this Venn diagram here, and we're told that events A and B are independent, events B and C are also independent, and we need to find the values of P, Q, and R. And then we will also determine if events A and C are independent. So let's start by trying to find the values of P, Q, and R. We are told that events A and B are independent, which means we can use the formula for the probability of A and B equaling the probability of A multiplied by the probability of B. So let's work out each of those probabilities. The probability of A is the sum of all of these probabilities here. So if we add all of those together, we'll find that this is equal to 0.65. The probability of B is the sum of all of these probabilities, which is this, and if we simplify, we'll end up with 0.49 plus P. Now we also need the probability of A and B, which is the overlapping section of these two circles, so these probabilities here. If we add those together, we end up with 0.39. Now we can use our formula for independence. The probability of A and B is the probability of A multiplied by the probability of B. So if we substitute these values in, we have 0.39 equals 0.65 multiplied by 0.49 plus P. So we end up with this equation here. We can divide both sides by 0.65. On the left, that will give you 0.6, and on the right, the 0.65 will cancel, so we just have 0.49 plus p. And subtracting 0.49 from both sides will give you p equals 0.11. So we found the value of p. So we can add that onto our Venn diagram. And we can also update this value for the probability of b. It's 0.49 plus p, so it's 0.49 plus 0.11, which is 0.6. So we've got the value of p, can we find the other two? Well, let's use the fact that we've been told that events b and c are also independent. We already have the probability of b, so we'll need the probability of c, which is the sum of the probabilities inside the c circle, which is all of these, which will simplify to give you 0.41 plus q. We also need the probability of b and c, which is the sum of the probabilities in the overlapping section of those two circles, so these two here. That's 0.2 plus 0.1, which is 0.3. We can then use the formula for independence again. The probability of b and c is the probability of b multiplied by the probability of c. So let's substitute in all of those values. That gives us this equation here. Dividing both sides by 0.6 will give you 0.5 equals, and on the right hand side the 0.6 will cancel, so 0.41 plus q. Subtracting 0.41 from both sides will give you q equals 0.09. So we can add this onto the Venn diagram and update our value for the probability of c. It's 0.41 plus q, so 0.41 plus 0.09, which is 0.5. So we've got the value of q, we just need the value of r. Well, we actually now have all of the probabilities inside the Venn diagram apart from r, so we know that all of them must add together to give 1. So if we add up every single probability, including r, this must equal 1. If you then simplify all of this, you get 0.95, so we have 0.95 plus r equals 1, and if you subtract 0.95 from both sides, you find that r is equal to 0.05. So r is equal to 0.05, and we've completed the first part of the question. In the second part of the question, we need to determine if events a and c are independent. So we need to test if the formula holds for these two events. We have the probability of a and the probability of c, but we don't have the probability of a and c yet. So we need to find this. That will be the sum of the probabilities in their overlap, so these ones here, which if we add together gives you 0.31. If these two events are independent, then this formula will be true. The probability of a and c is 0.31, the probability of a is 0.65, and the probability of c is 0.5. So let's see. We have 0.31 equals 0.65 multiplied by 0.5. If you multiply 0.65 and 0.5 together, you get 0.325, which is not equal to 0.31. We can therefore say that these events are not independent. Sometimes probability questions don't involve Venn diagrams at all. In this question here, 420 students from years 11, 12 and 13 were asked their favourite science, and here's a table of the results. One of the students is selected at random, and we are told that X, Y, and Z are the events the students were in years 11, 12, and 13 respectively, and also events B, C, and P were the events that the student's favourite subject was biology, chemistry, and physics. For the first question, we're asked to write down two events that are mutually exclusive. Remember, that's two events that cannot happen at the same time. Looking at the table here, we notice that year 11 and physics is 0. That means it's impossible to pick a student that was in year 11 whose favourite science was physics. That means event X, which is the event the student was in year 11, and event P, the event the student picked physics, cannot happen at the same time. So we would say events X and P are mutually exclusive. Now technically we could also pick any combination of events from X, Y, and Z. So X and Y are mutually exclusive since you can't select a student that's in year 11 and also in year 12 at the same time. Or for instance, events B and C. A student can't choose both biology and chemistry as their favourite science. For part B of this question, we need to show that Z and C are independent. So we're going to use that independence formula once again. We'll need to find the probability of Z and C, the probability of Z, and the probability of C. Event Z is the event the student was in year 13, and event C is the event that they picked chemistry. So let's have a look at the table for the event Z and C, so where both events happen at the same time, which is the students that are in year 13 who also picked chemistry, which is these 28 students here. Since there are 420 students altogether, the probability that we selected one of those must be 28 out of 420. For the probability of Z, we're just looking for students that are in year 13, so the total number of those students is 84 out of the same total 420, so it will be 84 out of 420. And for event C, which is just chemistry, we want the total number of students that selected chemistry, which is 140, out of the same total 420, so it's 140 out of 420. Now each of these probabilities can actually simplify. The first one will be 1/15th, the next one is 1/5, and the next one is 1/3. Since we've been asked to show these events are independent, we need to show that this formula holds. So the probability of Z and C, which is 1/15th, needs to be equal to the probability of Z, which is 1/5, multiplied by the probability of C, which is 1/3. And of course, 1/15th is the same as 1/5 multiplied by 1/3. So we've now shown that these two events are independent. For the next part of this question, instead of selecting one student, we're actually going to select 3 different students. The next question says to work out the probability that all 3 of these students chose the same subject. To do a question like this, we want to work out the probability of each of the outcomes where this is true. There are 3 ways in which all of the students could select the same subject. If all 3 of them selected biology, all 3 selected chemistry, or all 3 selected physics. So we just need to work out these probabilities, then add them together. The probability that the first student selected picked biology is the total number that picked biology, so 246, out of the total number of students, 420. So it'll just be 246 over 420. Now since we are selecting different students, we can no longer select that same student once again, which means the number of students to pick from that selected biology has decreased by 1, and also the total number of students that we can select from has also decreased by 1. So we multiply this by the probability that the second student also selected biology, which will be 245 now, out of 419. And for the third student, we also need to reduce these numbers once more. There is 1 fewer student who picked biology and 1 fewer students overall, so we would multiply this by 244 over 418. If you type this into your calculator, it will likely give you a decimal, so this number here. If we repeat the same process for chemistry, the total number of students selecting that was 140 out of 420, so it'll be 140 out of 420, and then we multiply this by the probability that the second student also selected chemistry, which once again we'll need to reduce these numbers by 1, so 139 over 419, and for the third student we multiply this by once again reducing these by 1, 138 over 418, which will give you this number here. And if you repeat the same process for physics, there were only 34 students that selected that one out of 420, so it's 34 out of 420, multiplied by 33 out of 419, multiplied by 32 out of 418, which gives you this number here. Now to find the probability that all students selected the same subject, we just add together these probabilities, which will give you this number here. Usually in your exam questions, you'll be told to round this off to a certain degree of accuracy. In this one, let's say it's 4 decimal places, which will be 0.2369. In the next part of the question, we're going to work out the probability that only one of the students selected is in year 11. So we could say that's the probability of yes, no, no, where yes means the student was in year 11 and no means they were not. It could also be the second student that's the one in year 11, which would be no, yes, no, or the third student that was in year 11, so no, no, yes. So we just need to work out these probabilities and add them together. There are 235 year 11 students, so the probability that the first student we select is in year 11 is 235 out of 420. We then need to multiply this by the probability the second student is not in year 11, so it must be one of these students here in year 12 or year 13. If we add those together, we get a total of 185. And since we haven't picked one of those students so far, it will still be 185, but out of 419 because we have removed one of the students, which was the year 11 that we picked first. And then we need to multiply this by the probability that the third student was also not in year 11. So far we've picked 2 students, one of them was in year 11 and one of them was not, which means there are now 184 students now not in year 11. So it's 184 out of 418 because we've removed another student. If you type this into your calculator, you'll get this number here. Now, when we do the next outcome, you might notice something interesting. So the probability that the first student is not in year 11 is from the 185 students out of the total number 420. The next student is going to be in year 11, and there are 235 of those, so we multiply this by 235 out of 419, since we've already removed one student, And for the final students, we will go back to one that's not in year 11, and since we've already removed one of those, there are now 184 out of the same total again, 418. That gives you this number here, which is the same as the previous outcome. And this will also happen with the final one. So not in year 11, we will have 185 out of 420. We multiply this by not in year 11 again, which will be 184 out of 419. And then the final student is in year 11, so 235 over 418. And this once again gives you the same number. So we just need to add these three numbers together, which is the same as multiplying this number by 3, which will give you this number here. So this is the answer to the question, and we'll round it to 4 decimal places once again, so 0.3262. We're going to do one more part to this question. Work out the probability that at least one student chose chemistry. When we say at least one student, we mean one or more students. So it could be that one student chose chemistry, or 2 students chose chemistry, or indeed all 3 students chose chemistry. This could be quite a lot of different outcomes. Often with a question that uses the words at least, it's actually easier to work out the opposite or the complement of this. So rather than working out at least one student, which is one or more, we could work out the probability that no students chose chemistry. We could then use the fact that the probability that at least one chose chemistry is equal to 1 subtract the probability that no students chose chemistry. So let's work out this probability instead. If the students did not choose chemistry, they must have chosen biology or physics. So if we add this number and this number together, we get a total number of students of 280 that did not choose chemistry. So the probability the first student we pick has not chose chemistry will be 280 out of 420. And then we multiply this by the probability that the second student also did not pick chemistry, which will now be 279 since we've already picked 1, out of 419. And for the third student, it will be 278 out of 418. If we do this on a calculator, you get this number here. So we can now say the probability that at least one chose chemistry is equal to 1 subtract this number here, which will give you 0.7048 if you round it to 4 decimal places. Thank you for watching this video, I hope you found it useful. Please subscribe so you don't miss out on my future videos, and why not try the exam questions in this video's description.